Welcome to the Passive House podcast, brought to you by Passive House Accelerator, a catalyst for zero carbon building. For news, inspiration, and connections from all flavors of Passive House, check out passivehouseaccelerator.com. Sign up to receive regular updates about events, get your technical questions answered, and contribute to the community forum. There's loads of free information for experienced professionals and people just starting out on their Passive House journey. We hope to see you at one of our construction tech or weekly global Passive House showcase webinars. In the meantime, here's this week's Passive House podcast. G'day and welcome back to the Passive House podcast. I'm Matthew Cuttler-Welsh, coming to you from Auckland, New Zealand.
And I'm Zach Semke, coming to you from Seattle, Washington.
How are you going, Zach?
I am doing well. We've had some clear weather, or at least just gray, not wet. So I've gotten to go running a little bit, which has been nice.
Nice.
How about you?
Yeah, good. It's settling a little bit. We've had a couple of storms come through. But this does tend to happen when people head back to work after Christmas, New Year break. The weather becomes really nice.
Right.
That's just the way it is. School kids, most schools are going back either this week or next week. So sort of getting back into the swing of things, into the year. Building sites starting up again. Those that did slow down. Although what I'm noticing is a lot of apartment buildings and higher density buildings, certainly around where I am, they don't seem to slow down much the last few years. Typically, building and construction pretty much closed down for most of January in Australia and New Zealand as builders kind of went off and had a holiday. But I think some of these bigger projects, they just push on through.
Too much pressure.
Yeah, stuff has kind of kept on rolling. And I think we're fairly fortunate to have got through a lot of the constraints around product material supply constraints, and there are still pressures there, and certainly some labour constraints. But other than that, things are trucking on. So busy times, but good. And I took some time out before I got back into the full swing of things to catch up with a few former colleagues and friends in the industry, and one of whom was our feature interview today, Jesse Clarke from Pro Clima in Australia, who got a lot of time and a lot of respect for Jesse. So we'll get into that shortly. But before we do, let's give a shout out to our sponsors.
Absolutely. So a big thank you to our founding sponsors, 475 High Performance Building Supply, Baxt Ingui Architects, Glavel Foam Glass Gravel, Minutair All-in-One HVAC and Dehumidification Units, Mitsubishi Electric Train HVAC US, Partel, Rockwell North America, Stocorp, and Zola Windows. Thanks as well to our champion sponsors, Icon Windows and Doors, Intelligent Membranes, Proseco, and Source 2050. And a big thank you to our stakeholder partner, NYSERDA, the New York State Energy Research and Development Authority.
Very good. All right. Jesse Clarke is, for me, someone who helped define what building science is really, especially in this part of the world. Currently, he is the Innovation and Research and Development Manager for Pro Clima, Australia and New Zealand. He's based in Sydney, Australia. He's also the chair of the Special Technical Group for Building Envelope Physics at ASHRAE, which is a very important organisation in Australia for refrigeration and air conditioning and heating. He is the director of the Insulation Academy in Australia, and has been involved in promoting building science and particularly moisture control in and around Australia for a number of years now. Very well respected within the industry, not just within the team at Pro Clima, but also beyond that, and the influence he's had on and is continuing to have on the building code, which we do touch on a little bit. That's one of Jesse's aims in life, is to change the building code, and he's kind of accepted, I think, that does take a little bit of time, and as much as we'd like that to move faster, I think Jesse's become a little bit pragmatic in the realization, the politics of kind of how to get change happening at a policy level. So I wanted to delve into a little bit of Jesse's background, how he got into doing what he does today, and also talk about some of the more recent and exciting resources that have become available on the Pro Clima website. So here he is from Sydney, Australia, Jesse Clarke. So why don't you start off by telling us how you got involved in building science in the first place?
Building science, all right. Goes back, I guess, to my childhood, really. It was growing up, I was the son of a builder. My brother's now a builder. But that's, I guess, where the interest in putting things together came from. And my dad was always a person that liked to do things properly. So if you talk about building science, he was always diving into the textbooks of, how do you build stuff properly, and what are the details and how does it work, sort of things. But I guess where I've gone is the next level after that. But I did an engineering degree at uni, and I guess that kicked it all off, because the engineers have inquisitive minds, and most people stop asking them why somewhere in their lifetime, but some people don't. And I guess I'm one of those people that hasn't, and that's where it takes you down the route of but why, and you almost end up in the meaning of life, right? So that process of asking the questions is where it all stemmed from. The engineering degree I did was actually in solar energy, like not related to buildings, but kind of related to buildings, so photovoltaics, and that took me into sustainable building consulting. Which then was about balancing heat loads on buildings. It's about how do you stop the heat loads and too much sun getting into all the glass boxes we build in Australia, and stopping the air conditioning energy use going up through the roof. So a lot about glass and glazing and shading, trying to prevent that solar heat gain. From there, I went into building products, and that's where it got interesting, because building products was more about details. It was about how do you put buildings together to make sure they work. And that's where all the moisture started coming in, because energy is one thing. You lose energy. Yeah, okay, my energy bill's a bit higher, but moisture is real liability.
Yeah.
Moisture, liquid water ingress, or even condensation and moisture accumulation through water vapor diffusion is also liability. And that's where I started getting into all this building science, because I was asked the question early on in my building products career, where can you safely use aluminium foils? I think I have an answer now. That's 10 years later, all right? And the answer is kind of nowhere.
Yeah. Which doesn't stop people from using them.
Which doesn't stop people from using them. If the regulations allow it to happen, it will happen, because it's a cost-driven scenario, and the foils are cheaper, generally speaking. So that's where we're at. But if you want to build something properly, it's not going to be cheaper. Well, the capital cost is not going to be cheaper, and that's where smart people start looking at what is the lifetime cost, or the lifetime cost of ownership of assets, and all that sort of issues that you go through in the Passive House courses, which is how much is it really costing us over the lifetime of that building. And building something better generally yields better buildings, and in that process they last longer, and you use less energy.
Just picking up on the foil issue, my understanding is that people use it because it's seen as a cheap form of relatively good insulation. Well, when I say relatively good, I mean for the size and cost. Is it primarily as an insulating product?
Yeah, so what happened, this is something I'm trying to flip on its head, actually, which in Australia, there was early research from US, which was around the R values attributed to aluminium foils and reflective air spaces. And by reflective air spaces, I mean air gaps that are adjacent to a low emittance aluminium surface. And it's not that you don't get a reduction in heat flow by doing that. It's just that the Australian Building Code copied, or the standards in Australia copied this US research that started off in 1954, I believe, Housing Research Paper number 32 from US, and it assigned all these R values, and then it picked up on that, and ASHRAE picked up on that, and they assigned R values to air gaps. Then that came into the Australian standards, into AS 4859, which was a calculation methodology for R values. Then, yeah, it becomes a cheap way of getting R values in structures, so a cheap way of meeting building code.
So did you say that it started as a way to stop air, but then became a means of reflective R value?
Not exactly. To get an R value out of a reflective surface, you have to have an air gap adjacent to that reflective surface.
Right.
So it's because it's working on radiative heat transfer, and radiative heat transfer happens through air.
Yeah.
So if you've got an aluminium surface hard up against another product, it does nothing. Absolutely zero. Except for trapping moisture behind it.
Which is strange, because that's where the evolution of that product has gone, to be a laminate of other materials.
Yes, correct. So there's lots of applications where it is facing into an air gap, so you would get some R value out of it. But the other applications, you've got insulation jammed up hard against the reflective surface. It's useless. And the other thing is, all the research was always based on still air, not moving air. So there's a lot of assumptions that have been built on the decades that have not really been answered that well. But the really big problem is not, the biggest problem we got in all this is people chasing the R values and the thermal performance, energy efficiency, without due respect for the perverse outcomes or side effects, which is the moisture side.
Is there also a big element of people just kind of doing things the way they've always been done? At some point there must have been someone who thought, this is what they're doing overseas, therefore foil must be a good idea, and then it kind of becomes entrenched as the way things are done. And is that kind of what you're seeing now, and trying to turn that around and saying, hey, well, this perhaps isn't the best approach?
Well, exactly. I guess, like I said early on, I never stopped asking why. So, the fundamental basis of science is to always ask why.
Mm-hmm.
And it's like, well, how do we end up that in our code? Why is the US moving away from these foil barriers? Why are they talking about vapor permeability? Why does Europe talk about vapor permeability? Why do we not talk about it? Because we're different. That's European, that's American, and for some reason we're uniquely different here.
Yeah.
Well, what's the only unique difference is not the science. The unique difference is the codes and standards that attribute or award certain building practices.
Yeah.
And they award that through, like you said earlier, cheap R values.
Right. Just before we move on from foil, because I don't want to spend the whole time talking about that, but I know that perforating it has been one way to try and get, I guess, the benefits of the reflectance, but allow moisture to get through. Is that why we sometimes see perforated foil, and does that work?
Yeah, and this is funny, because this is a battle I've been fighting for many years, but also with the up at the building codes level, trying to get them to understand, if you put holes in something, yes, you allow water vapor through, but it's not going to do much for weatherproofing, because you've got literally holes that are going to leak water all through them.
Mm-hmm.
And under wind pressure, you just force all the water through those holes. So back to the fundamental basis, why do we put membranes in buildings? Or why do we even need them? Why don't we just leave them out? Because the most vapor permeable membrane you can get is no membrane.
Mm-hmm.
So that was the question.
But membranes are important for not weatherproofing, but being weather resistive.
Yeah.
On the outside.
if I was in the US, I'd be talking about weatherization or weatherproofing or whatever you want to call it. But yes, absolutely. So the fundamental basis why you want to put a membrane in behind the cladding, whether it's a roof or a wall, is to improve the weather tightness of the building. And those membranes need to be there to have properly weather-tight buildings.
Mm-hmm.
So if you take that as a priority to make buildings weathertight under driving rain, when you've got lots of wind and rain at the same time, then you go, okay, I need the membrane. So now how do I make it as vapor permeable as possible to make sure that the systems can dry out as much as possible?
Yeah.
But there's also, just on that last one, there's also limitations to that, because if you make it too permeable, you trade off other things like durability or the air tightness properties or even the water holdout.
Right. And that's all on the outside. Then you've got other things going on the inside layer of the building envelope as well. So you want to have a membrane there for vapor control and air tightness, but for different reasons. Yeah,
and then you get into this relatively new concept for Australia, which is vapor control layers on the inside of the building.
Mm-hmm.
And that blows a lot of people's mind in this part of the world, because it's like, you're putting a membrane where? On the inside.
Right.
Why would you do that? This is a sark-in, and sark-in, by historically, the term sark in Australia is talking about a secondary layer behind the cladding that sheds water.
Yeah.
And that's what we talk about in Australia, sark-in.
I think I really like that underlying continual questioning of why, because what we've ended up with just by talking through it is something that started out as insulation, because the purpose was R value, but then it becomes relevant to weather tightness and air and vapor control. So if you're putting something in there thinking that it's there for one reason but is actually impacting something else, that can lead to problems. I guess a big challenge for the industry is that often we don't like to think about things. We just like to do what we know to be true, or what we've always done in the past. So having to rethink everything every time we design a building, that sounds a bit like hard work.
Absolutely. And that's absolutely right. Or thinking in general is hard.
Yeah.
It's easier not to think. So what happens, though, is people are making money. People are making money out of the way we currently do things. So if people are making money, they want to keep it the same. You don't want to change things. So that's a big driver. But one of the reasons I believe that we ended up down that route of the thermal performance of membranes being the top of the pile, or the main performance characteristic, is because the membrane standard is actually developed by the Insulation Committee in Australia.
Right.
So the insulation guys obviously put the focus onto the thermal performance of the membranes, not the weatherproofing.
Yeah.
So then when you look at international building science, it's like, well, hang on, moisture is king. You always deal with the moisture, and then we'll worry about the thermal performance. So we deal with the external rain, make sure it's weathertight, and we deal with the vapor diffusion issues, and make sure we don't get accumulation of moisture, condensation, and mold growth.
Do you not think there's also an element of just more interest in energy in general? I mean, you started out in energy. You didn't start out in health or building resilience.
Yeah.
So do you think that more people are just naturally attracted to wanting to make buildings more energy efficient and not necessarily think about health and durability?
Absolutely, because it's it starts with energy, obviously, because people got commitments, international commitments to hit carbon commitments around reduction targets. So the government's put in energy efficiency requirements, more insulation, which is a great thing. Don't get me wrong, put more insulation in, keep jamming as much as you can in, but let's design it right, because the laws of physics say for every action there's a equal and opposite reaction, right?
Mm-hmm.
So how can you just make a mass change, pull a huge regulatory lever with no side effects?
Mm-hmm.
The side effects is health and durability. But if you address that and you know what's happening, then there is no problem. Because all this fear of sick buildings and everything, I mean, the opposite to fear is knowledge. And if you have the knowledge, you won't get a sick building. You'll get energy efficiency, you'll get health, and you'll get durability, all in well-designed buildings.
Yeah.
If you put the focus just onto energy, then yes, you can potentially create a bigger problem.
How do you feel about where you are now in relation to when you set out to learn about solar PV and put solar panels on roofs across Australia? I imagine it's not exactly where you thought you might be, but how do you feel about that?
It's interesting because I feel like I'm sort of where I was at uni going, oh, what's the next big thing? And that's why I did a degree in solar energy. I said, this is going to be big. But I was young and naive. I thought 3 years was a long time. So, you'd have $1 billion industry in 3 years' time when I finished uni. But it wasn't so the case because I was the first year that went through the photovoltaics engineering degree at University of New South Wales. So we're the first batch to come out of that. And that's why I ended up in sustainable building consulting because there wasn't a lot of jobs. The industry was small here. I mean, Germany was going gangbusters because of government intervention. So there was probably opportunities in Germany if I had spoken German better at the time. But I stayed here in Australia and ended up in sustainable building design. But I see myself in the same position where this is the early days of that growth. And you're like, if you stick with it, it will be big. And it will be, and it is getting bigger. So people are catching on, but it takes time. There's a lot of people to learn stuff. And the information and knowledge has to infuse or diffuse through society, basically.
And what is that that's getting bigger? How do you sum it up?
Well, the healthy building movement, I guess, which is what was not on the radar of certain government organisations or certain industry bodies. They're all pushing the energy efficiency. So it's the Energy Efficiency Council, more insulation, more renewable energy. That's all good things. But then it's all of a sudden, hey, is there a negative side to doing some of these things? Yeah. But people don't necessarily want to see that, or they don't want to highlight something. If you're pushing a certain agenda, you don't want to highlight something else perverse that might be happening. Yeah. But I guess myself is going, well, okay, is there a problem? Let's go solve it.
Because is there a sustainable engineering or a sustainability degree now? Is there a recognised profession?
There's
or a
renewable energy engineering. There's architectural science degrees and masters at certain unis around Australia. So it's coming. It's coming. Yeah, so that new wave of graduates in architectural science, I think, is going to be very useful.
As distinct from professional architect of just doing, well, not just, but doing the more traditional design of the aesthetics and making the building work aesthetically and just function. So architectural science was that different from building science?
I'm still trying to work that out, but I think the focus is more on that technical architectural side. So taking the sole emphasis of making something aesthetically pleasing, which is important. Don't get me wrong, but how things actually work and what's happening inside the structure. Inside the building and how all these components go together to try and meet all these overlaying or overlapping requirements in the building code. But the building code itself has so many conflicting requirements that to follow the deemed to satisfy or recipe that they prescribe is probably going to end up in a disaster. So then you start to talk about, well, okay, how do you do it right? Well, then you have to start to understand all these complex interactions and try and do build buildings to your own recipe, which is a verified or a verification pathway where you're actually pushing the boundaries of knowledge, and you're starting to push down the roots of things like Passive House and saying, well, how do we end up at this solution that has these sort of 5 key principles? How did the Europeans end up at this? How did the Americans and FIAS, how did they arrive at adopting that sort of thinking as well? Because in the process, or what I've often called the cascade of intervention, which starts with insulating buildings. So agreements or commitments to reduce carbon, you jam more insulation in buildings into the standard construction process and go, whoops, created a problem. How do I fix that problem? Okay, we put vapor permeable membranes on. Well, that's not good enough. We've still got problems. We created a more airtight building because we've tried to weatherproof these things. Oh, hang on, we need some ventilation. Okay, add some ventilation. And you go through the process. Oh, hang on, we've still got these stripes of mold on the inside of our plasterboard. What's happening? Oh, that's thermal bridging. Oh, okay, let's eliminate thermal bridging as well. And eventually you end up with something that's like, well, hang on, they're the passive house principles.
Yeah.
Oh, someone worked this out already. Oh, yeah, they did.
Like 30 years ago.
Yeah, exactly. So, but it's that you got to go through the pain, and you got to create the problem before you can solve it. So the building code changes, and it's incremental changes that create a problem that then you solve. And every 3-year cycle in Australia, you've got a chance to another bite at the cherry to make something a bit better.
It sounds painful. Is that your mature outlook now that it's just a process that you've got to go through? Is there any way of short-circuiting that 30-year learning process?
If I could work out, how to put myself in some sort of cryogenic freeze chamber and then just thaw myself out in 30 years, I reckon that would be the best way.
For you, that'd be right for you.
Yeah. And let everyone else work it out.
Right.
Yeah. No, but it's there. We know it. So I say we collectively, certain people know it, and advocates like yourself, people that are out there trying to push the right way of doing things know it because they're asking the questions of why. They're not just saying, oh, okay, I'll just keep building the same old way, and that's the way my father and my grandfather and whoever else did it.
So what are some of the successes that you've had because you have impacted the code? What are some of the successes as you see it in Australia?
So I guess it started way back in about 2000, and I guess, or probably earlier than that, 2010, where the learning curve started in the building products, in my building products part of my career, which was how do you put things together better? And the fundamental question that was asked to me, where can you safely use vapor barriers, which then sent me down the building science rabbit hole. Mm-hmm. I'm still stuck in the rabbit hole. I think I'm going deeper and deeper, and I don't think I'm ever going to come out. But in that building science rabbit hole, it was about, okay, vapor barriers, how do that work? Okay, membranes are good. They make a building more airtight. Oh, how can you achieve airtight buildings? Oh, hang on, there's lots of value propositions to airtightness. Airtightness is not just about energy efficiency. It provides better acoustics. Oh, if you make buildings more airtight and seal up fire-rated walls, they actually act like a fire-rated wall. They don't provide pathways for fire to spread. So there's all these overlapping value propositions to airtightness. They stop water vapor going where you don't want water vapor to go. So you don't get all this air transported water vapor leaking up into your ceiling cavities and creating problems for you. So making more airtight buildings made sense. So I started advocating for airtightness. And I said, well, okay, if I'm going to advocate for airtightness, I know that Europe created a problem for themselves. I know the UK created a problem for themselves. I know that the Americans have had problems in terms of creating more airtight buildings and trapping moisture. So then it was, how do we stop this? Oh, it's okay. The next thing. Okay, let's speak to Fraunhofer. Fraunhofer know what they're talking about. So I went over to the Institute for Building Physics and started talking to Hartwig Kunzel over a decade ago. And that's when got into all the moisture management. It was all about selecting materials and making sure that you can put material layers and vapor control layers and vapor permeability and have all these layers in the right position in the building structure. So that's where, hang on, what was I talking about now? So the big successes. Yeah, so the big success was getting airtightness into the building code. And that's where I started looking, okay, I've put airtightness in the building code, which was based off a lot of work that happened through the Australian Institute of Refrigeration and Heating. Mm-hmm. And that we drafted a cost-benefit analysis to say that airtightness is good from an energy perspective. And then, that next step was how do we stop the perverse outcomes, and got into the moisture side of things. So then all this work through AERA and through the Fraunhofer Institute, we said, oh, hang on, ASHRAE 160. That's a moisture control design analysis for buildings in the US. How does that standard work? Oh, okay, that standard works by allowing engineers to calculate what material should be used in what location in buildings to be able to prevent perverse outcomes in airtight structures. Okay, we need that one. So we worked through AERA and we adopted that ASHRAE standard into Australia through the Australian Institute of Refrigeration and Heating. Then we put it forward to the Building Codes Board and said, you need this. We need this as a verification pathway so engineers can do calculations. So it got adopted in the 2022 code. So 2019, we had airtightness. 2022 code, we had moisture management. So the industry is kind of in a evolution, I guess, a steep learning phase.
Yeah. How
does this all come together?
Yeah.
How do we get this air tightness and moisture management to come together?
And you're contributing to that through teaching WFOE?
So WFOE is happening. So I've been teaching WFOE for quite a few years now, five odd years at Pro Clima here, and WFOE is a software package that you can use with the AERA DA07 as a compliance pathway for the building code, but you can also use it to just work out how high performance, highly insulated passive house construction systems will work in different climates. And Australia has a really wicked problem. And the wicked problem is a bit like the US problem, which is the range of climate zones from tropical, humid climates all the way down to, alpine, freezing cold climates.
Yeah.
And that presents a problem because there's no one solution fits all.
But that's where people need to do a bit of analysis, and you got the tools to do that. I remember the very early days, a bit of a challenge explaining to people what WFOE was and why they should bother. But are you seeing some uptake now and people realising its usefulness?
Yes. So there definitely is an uptake happening, and that uptake in Australia has largely been, I think recently there's been a big uptake because of the Building Code 2022, which mentions the AERA DA07.
So which is forced to.
Well, if you want someone to read a document, I think the building codes, the Australian Building Code would probably be one of the most read documents in the country. Right. You'll have millions of people reading it, right?
Right.
So they see this AERA DA07, start asking questions, and then, okay, what's it all about? And then takes them down the route of looking for WFOE.
Yeah. I just want to quickly mention a couple other resources you got available. You got the Blue Book, which you've put a lot of work into, and also the Australian Moisture Study.
Yeah.
What are the differences between those two documents? What do they do?
The Pro Clima Blue Book was drafted because I got asked so many questions when I was doing the WFOE training about, where do I need to look at, where's the problem going to occur in the construction system?
Right.
So in that Blue Book, there's probably 100 odd, I don't know how many there are, 100 odd systems that say, if you're going to analyze this system in WFOE, you might want to look at mold growth at this location, this location, this location, and you might want to assess for water leaks because you've got no drained and ventilated cavities, so you're probably going to get water in there. Mm-hmm. And it's a guide on just what you should put into WFOE. So it was the first step in an evolution to get to a holistic national answer. One day, all those systems will be calculated out with a answer in every single climate zone.
Yep.
The Australia study was a document that's been a long time in the making, which has probably been about 3 or 4 years in the pipeline, and it is a study into air tightness and moisture management in Australia. So it looks at more the residential context, but how you should construct the wall systems to stop moisture accumulation, why air tightness is good, not just from an energy efficiency, but why air tightness is good to control that water vapor, stop it going into your construction systems and creating problems, and how you actually design a roof properly, which there is no specific answer in specific climates yet, but to have a properly ventilated roof system where you've got the structured ventilation in the right place behind the cladding is critically important. And in Australia, we've got some really weird construction practices. All the rest of the world would think they're weird, but they're a legacy. They've been doing it for 30, 40 years, but we know that these properly structured ventilated roof systems are the way to build. So it talks a bit about that. So there's a lot. There's moisture management in walls. There's roof systems and how to build them properly. There's stuff about mold and what all this mold calculations are all about. There's stuff about air tightness. and it's in the context of Australia and where Australia's currently at, and the discussions that are happening around healthy, durable, and energy efficient buildings.
Awesome. We'll put links up to those so people can find them. Just to finish off, what's going on in 2023? What do you see? Predictions for this year? Where would you like things to go in the world of building science in Australia?
There's some interesting stuff happening in the energy efficiency calculations for residential in the National House Energy Rating Scheme, because they're starting to load into that the ability to do airtightness calculations, or ACH 50,
right,
and include that in the calculations, which is potentially a game changer if it becomes regulated, because all of a sudden you can get credit for making a more airtight building. If you can get credit for making a more airtight building, then it's a bit like the aluminium foils. It becomes another arrow in the quiver to potentially make a building or meet the regulations in a cheaper fashion. So that in itself could create a bigger market for airtightness.
Yeah.
Which means that you also have to consider the other things which we talked about, which is water vapor diffusion and water vapor management, as well as indoor ventilation strategies and all that sort of stuff. So that's the residential context. In the commercial context, we've got things changing around thermal bridging, and we like to build a lot of commercial structures, multi-residential buildings out of steel frames.
Mm-hmm.
But that presents a problem, clearly, for thermal bridging. So the other thing is moisture management in the commercial facades. And the rest of the world and the people, if anyone listens to this international, will go, well, the answer's obvious, right? Put the insulation on the outside of the structure. Yes, it is obvious, but we've got to get there. So I think we're going to start to see that happening, insulation going on the outside of structures. And to me, that's fantastic. If we start to see more of that in 2023, I'll be happy.
Yeah. Good stuff. Awesome. Hey, well, thank you for your time today, but also all the great work that you have put in over the many years. I know it can be frustrating sometimes, but I hope that you genuinely do feel that you're making a positive impact, because it obviously is starting to happen with those codes coming through and changes to the building code. So keep up the good work.
Yeah, and someone said to me recently, a very well-respected person in the industry said to me, it's people often overestimate what they can do in 1 year, underestimate what you can do in 10 years.
Absolutely. Keep it up.
All right. Thanks, Matt.
And that was Jesse Clarke, who's the Innovation and Research and Development Manager for Pro Clima, as well as being involved on a number of boards, particularly the Special Technical Group for Building Envelope Physics at ASHRAE, and also the Director of the Insulation Academy. What do you think, Zach?
Oh, it was excellent. Thanks for doing this interview. I love his asking of why this line of inquiry that he brings to probably every aspect of his life, it would be my guess, but certainly building science. And I mean, it was interesting that kind of that process of discovery and kind of was encapsulated a little bit in your conversation around foils at the very beginning of the interview.
Yeah.
And then you guys just dived, so much deeper into that exploration of like what you referred to as the cascade of interventions, which I've heard around healthcare, right? With the cascade of intervention when you start medicating for problems, actually. Mm-hmm. And so starting with insulation and then going to like an examination of vapor permeability, and then, what about thermal breaks? And I love that moment where it says that you end up at Pascal's principles and, someone worked this out already.
Yeah.
We all go through this, I think, this process or need to. and each region definitely seems like it needs to do it itself, right?
Yeah.
You can't just be like, oh, well, it's the Germans, or oh, that's the Americans.
Yeah.
So
which is frustrating for
Yeah.
people that have, I guess, have gone through that process in some way themselves, to then watch other people do things like put foil on a building just because of the way it's been done, it's the way they've been taught, and realize that there's at least 2 or 3 steps that they've got to go through in order to get to the point of having good weather tightness on the outside, air and vapor control on the inside, and how that the system works. And like you say, that cascade of lines of defense and building up the whole system is not an easy thing to be able to just explain in one hit. I mean, Jesse's done quite a good job of that from an education point of view, and as well as his work in policy. He is a very good presenter and has run training courses, and he runs WWOOFy training in this part of the world. I think they have some coming up soon after this will come out. So if you are interested in learning about hygrothermal modeling, then jump on to through the Pro Clima website, and should be able to find those courses. But yeah, that questioning of why, I think, is really important, and Jesse is very, very good at that. And it often comes when it's a bad practice. The answer usually ends up as, oh, well, that's just the way that we've done it, or that's the way we've been taught. And there may have been a grain of sensibility to that originally for solving a particular problem, but then if it's just carried through without much thought about, do we still have that problem, or what other problems are being caused by that intervention, that's when we've ended up with mold and interstitial moisture and all these other issues, which, like you say, are not unique, and they're not new problems. These are problems that others have faced in other parts of the world. So in conversations that Jesse and I have had previously, we've come to the realization that our role has been to just fast track that learning process, because we don't think that it's possible to short circuit it and say, well, let's just wholesale adopt passive house into Australia, because you do get a lot of that pushback, and that's okay, because people have got to kind of go on that journey. But if we can speed that journey up, then that's going to be better for everyone, so that we don't have to take 30 years to come to the same result ourselves.
Exactly. I mean, I think that's the cool thing about passive house projects too, and I think, like, in a relatively new market where the passive house movement is still in some of its early stages, like in Australia and New Zealand, and honestly also like in the Pacific Northwest. These individual case studies and proofs of concept that each of these buildings represents are really powerful. So I think it can be frustrating to see the growth be slow, but they're powerful in a number of ways. I think they're powerful to speed up that learning process that you're talking about. They're also, I think, really key touch points for the process of code development and code evolution. Because you can say, look, it works right here. It doesn't just work in Germany or Vancouver, BC. It works here in Australia, and we can prove it. And all these pieces are working together. The systems are working together. It's durable. It's safe. That there's a kind of a ratcheting effect that can happen, I think, with building code and high performance building. And it's easy to forget the power of those examples. And ultimately, code has so much power. Like, that's where, I mean, market adoption is important, and we want to see that, and we need to prove that these are effective and cost effective. But if we can make progress in code, then that's where everything changes.
Brings up the bottom as well as inspiring the top. Yeah, absolutely. And that's where Jesse and some of his other colleagues, people like Sean Maxwell, another former colleague, is really driving the airtightness agenda, have had success. And it's sort of like small steps, but just kind of introducing these terms, getting them written, getting them formally into clauses within those codes, and then just kind of ratcheting it up over time. And that is how to have that success over a long period. I think Jesse's pathway is also a good analogy to a lot of people's thinking around sustainability, because going back to when he first started, he thought the solar panels were going to be the solution. His first foray into work was around selling and installing solar panels on roofs in Australia, which is been relatively successful. There's a lot of PV photovoltaics in that country, but over his working career has come to the realization that the real building science is where you can have a real change, and that's more about the envelope and looking at the efficiency rather than just the energy generation. And I think that's where a lot of people start when they first think about sustainable buildings or eco buildings. They think, put some solar panels on the roof. But then you delve into the details and realize that the envelope is kind of where it's at, both from a performance, energy efficiency, but also particularly a health aspect. And that's been kind of Jesse's own trajectory, and then to where he is today as one of, I would argue, one of Australia's leading building physicists and building scientists.
Yeah, that reminds me of the old kind of passive house practitioner adage around net zero, the net zero target, and the danger of a little bit of with not focusing on the envelope is that a crappy building with a bunch of solar panels on it is still just a crappy building.
Yeah.
So this ended, but with the energy efficiency intervention that is so critically important for our climate goals and all sorts of energy, addressing energy poverty and also all these other reasons, then we just need to then ask why around the vapor and moisture and thermal breaks and all that. So
just want to point out a couple of great resources that Jesse has been very instrumental in putting together. One is they call it the Pro Clima Australia study. It's a textbook basically on weather tightness and how it relates to warmer climates in particular. So definitely check that out, and it's free. So you can find that proclima.com.au, and also the Blue Book, which addresses a problem that Jesse recognised as a result of doing lots of WWOOFy training. That hygrothermal modelling, particularly using WWOOFy, is amazingly powerful, but can be very heavily skewed. The results can be very heavily skewed by some of the assumptions that you make. There's some quite big sensitivities in there with how much ventilation, for example, you assume in a cavity, whether it's on a roof or on a wall. So Jesse's tried to get some consistency or some recommendations of standardized assumptions for the Australian climate and would also translate to New Zealand climate. So as the use of hygrothermal modelling increases, and specifically WWOOFy in this part of the world, it's a really helpful guide to get people started, because that can be quite overwhelming as a piece of software. And this is just a bit of a guide of what systems would work in different climate zones across Australia, and also some guidance on how to model those so that we're all modeling them in a relatively consistent manner. So check that out. That's the Blue Book, and also the Pro Clima Australia study, both available for free at proclima.com.au. Awesome. All right. What events we got coming up?
Yeah, so we're in the thick of it. And I know this hasn't been great for the Australian or New Zealand audience, this change in the time, but it's a lot easier for people in North America to get there during the daytime. So this change to the noon Eastern slot has been, I think, great for those in North America and Europe. But the next episode of Passive House Accelerator Live is February 1st. It's our first episode of the 101 series. So this is going to be presented by Michael Ingui on February 1st. And it is 10 steps to designing your first passive house, tips and tricks from an architect. So the day before, so this will be on Tuesday, our time in North America. So that is Wednesday for you in New Zealand and Australia. We have a component spotlight presented by Coltraco Ultrasonics. And Coltraco is a sponsor of the accelerator and has created this new device called the Portascanner Airtight, which is a ultrasound leak detector. So there'll be the title of this component spotlight is Achieving Passive House Levels of Airtightness with the Portascanner Airtight device, and it should be really interesting. This is pretty brand new technology for us in Passive House. Yeah. And what else? Registrations are open for the Passive House Institute's International Passive House Conference that happens, I believe, March 10th and 11th in Wiesbaden, Germany. So don't miss that. We'd love to see you there. And all sorts of other things coming up in the Passive House world that we will provide links to in the show notes.
Awesome. And we can always watch those videos. If we don't get there live in the middle of the night, we can always catch up on those episodes afterwards and check out that great content. That's all there on passivehouseaccelerator.com. There's heaps and heaps of resources there and some great videos, magazine or articles, pictures, and also check out links to all our great sponsors, including Source 2050. We've got some great information on there as well.
We had a longtime community member, Barbara in Oz, join us from Australia this morning. So she was up at 3:50 in the morning. Yes. Well, it was a construction tech episode about HVAC design. She's got her own house project that she's working on. So she was very motivated to you learn as much as she can going into that project. So anyway, it was great to have her there. Yeah. Die hard.
All right. Well, thank you, Zach. Good to catch up. We've got some other great interviews coming up, so I look forward to bringing you those, and we'll be back again next week on the Passive House Podcast.